Well, good afternoon all. It is Rob here. Hope you're all well. Again, welcome to part two of this hydronics training course, and we're concentrating at the beginning at the moment on heat loss calculations. I'm recording this now on Saturday the 15th of February 2025 at about 4:45 in the afternoon. This will be a shorter tutorial than the one that we did the other day, and this kind of finishes off the longhand heat loss calculations of heat loss, but there's quite a few things to discuss here, so we'll crack on and get through it. Now, if you remember, in part one we had quite an interesting conversation at the end of it regarding this particular slide that we're showing on here, and we talked about the grant scheme. We talked about whether a property is heat pump ready and whether there are some low-hanging fruit that we could change, and so we did on this one, and we did a couple of examples of changing the windows with this from a U value there of 4.8 to 1.6, and I think we had the roof insulation that we changed from 2.0, as you can see right there, to 0.14. I think it worked out with 300 millimeters of mineral wool quilt insulation. So you can see those low-hanging fruit really changed things for us, and it made it a lot better. So it actually took our heat loss down from 17.9 kilowatts of a fabric heat loss to just over 6. I think it was literally just about 6.1 kilowatts. So it changed the whole benchmark of what we were trying to start this calculation from, and what we could actually specify as a heat source for this building once we'd done those fabric upgrades, which I think was a very, very good idea, and to me shows good due diligence with surveying in buildings like this. So if we move on now, we did say, is that it? And no, it's not. So we've now got to talk about air change rates, and air change rates are they're a subject that recently has come to a lot of debate over air change rates, because the current mathematics that are there on the guidance for it, they are pretty much always over-egged. They're oversized for what they need to be. And so what a lot of people are tending to do now is actually go and get either pulse testing or HTC testing, which is heat transfer coefficient testing. You can get these companies like Build Test Solutions and a few others out there that do this, and say, I'm not sponsored by any of these people at all. This is just purely guys that I've met in the industry over time. But to get a heat transfer coefficient calculation done, the only caveat for that is that you need around 7 delta T between inside temperature and outside temperature. So it does make it fairly seasonal, but it is very, very accurate to do a measurement. Or you have the pulse testing now, which can also be done. So a very, very good idea to think about these things. You can get a blower door test done as well at 50 pascals to test the air permeability of the building. And on various software now that complies with EN12831, you can input that whole house air change rate down into the software, which will give you a much better understanding and a much more accurate assessment of your heat loss of the building, of energy losing that building in real time. But I'll show you now the longhand calculations of doing this, which you can use in any environment, and you can change. And all you'd need to do is change the air change rate per hour to make it correct. But I'll go through all of that with you now, so you've got it, and then it's there forever, and you can use it whenever you like. So here we have a list of standard air change rates that are straight from the CIBSE guide. We have 3 different categories at the moment. We have a category A, which is pre-2000, so any buildings that were built before 2000, and the air change rates that were calculated out by CIBSE at that point in time, and that was part of the building regulations. We then tightened up our buildings between 2000 and 2006, so that was category B, and then we tightened them up again in category 6 post 2006. They have been done again, but the air change rates have not changed very much at all. But you can also customize these rates, and that is something that you can do, as we just said, through blower door tests or through pulse testing. And I would certainly recommend going down that road now. I think the price for getting these pulse tests and blower door tests has come down dramatically over the last few years, and if you've got a reasonably large project to do that you're bespoke installing a heating system to, I would highly recommend that you go and get a blower door test done or a pulse test done to get your calculations correct. But this is the list that we had from back in the day. This is straight from CIBSE guide, and you can see there's a couple of things that we used to do, and we spoke earlier on about design temperatures, and you can see that before 2000, before the year 2000, just here, we were sizing different rooms. You can see all these room names down here. We were sizing them at internal design temperatures or room temperatures at different temperatures, like all bedrooms at 18, storerooms at 18, those sorts of things there. So we had that. Once we moved on past 2000, everything started to get designed to one set degree, on one same degree everywhere, which kind of makes sense. And these are your VCR rates, so your ventilation change rates within your buildings. But you can see what has happened as well. Look how much some of these have come down over that time. So before 2000, we had ventilation change rates of 1.5 air changes per hour in a living room, and that's now dropped to 1 and now half after 2006, as buildings have got tighter, as our insulation has got better and our build quality has gone up. So these are the regulations, but they don't necessarily represent real world values. And this is what the big debate on social media and in various engineering forums and everything, this is what we all discuss, of whether CIBSE got these figures close enough or not. Now, you'll find in a lot of properties, even now, they have either log burners installed, or they'll have open fireplaces or things along those lines. Now, if it's a sealed log burner, it generally seals the room up, and so you don't get any additional air change rates that you need to add on to the system. But if you've got an open fireplace, like a lot of people have, it can double the air changes within that room. So maybe from 1.5 to 3, or something along those lines of those air changes that are going. So what I would always recommend that people do, if you and these are very, very cheap to get hold of, you can buy them online very, very easily. They're called chimney balloons, and you can buy them. I've got one at my house, and it's I've got a leather one, which you basically, once the fire is out of use, you would poke this balloon into the chimney void, and you pump it up with a foot pump, and it seals that chimney completely. It gives you a real good seal between that. That keeps your air change rates right the way down. And then I have a little sticker on mine, which I put down, which reminds me that the balloon is actually sitting in place, not to try and light a fire, obviously, it's there. But if I don't, and I have some friends around or something, or we choose to have a fire one evening, or something along those lines, then I just remove the balloon, and then that goes in. And I've said it on many occasions. My fire in my house, it goes on, and within an hour, all my heating has gone off. So it's obviously, it heats the whole house and brings the thermal mass of the building up to quite a high temperature quite quickly. But these are the rates that we would work on longhand calculations, and this would be the only one that changes as we move forward in this final equation of a longhand heat loss calculation. So we've done all the fabric heat loss calculations, but there's a little bit more to explain and describe as we move forward. So again, you've obviously got this slide now. You can pause it, take a screenshot, do whatever it is that you want to do, so you've got all of these. And remember that this is the British standard that we work to, which is BS EN12831. So this is a constant. This is the third constant that we have. We had the indoor and outdoor surface resistances overall on the calculations on fabric heat losses. This now is the third and final constant that we would use. It's 0.33 watts per cubic meter, not square meter, per cubic meter Kelvin. And what does this figure actually represent? Well, this represents the specific heat capacity and density of air under typical conditions. So if we look at the next slide, you can see that this is exactly what it means. It's a constant in the next equation, and we'll use this as we move forward. But so there's quite a few caveats, and I want to just try and do it and play around with a couple of these figures, so you can get an understanding of how much air change rates can really affect your end heat loss calculation, because they add quite a lot on. So the equation is your 0.33 constant, which is what we have. So that's I've written the equation down here. So it's 0.33 times the volume of your air, the volume of the room, times the volume of the room, times the number of air changes, which we just discussed on the previous slide. So whether it be 1.5 or 1 or 0.5 or whatever it is. And then times your delta T. And the delta T we set as before what your indoor design temperature is to your outside design temperature, your ODT. And in this case, it was -2. It could be changing all over the place, for whatever, whereabouts you live and whatever postcode you live within the country. So that's very important to always remember. But let's have a look at the equation and see what we actually had. So we had a fabric heat loss of 17,951 watts, but we'll try that again in a minute with our 6 kilowatt heat loss. That was the revised kilowatt heat loss, to see where we're going. So if we pull up our calculator and we have a look at what we've got here. So we've done, you can see on the number of air change rates, we've just taken the whole of this house as 1.5. Now that would change as different rooms, and we'll try that in a second and see what we're going on. So we had our floor areas were 160 square meters in total. We need to find the volume, so we multiply by the ceiling height, say 2.4. So that would give us 384 cubic meters of that building. So the equation is 0.33 times 384 cubic meters times the number of air changes times your delta T. Now in this situation, or this scenario, it gives us 4,371 watts. Now, what if we had a blower door test there, or we actually realised, or we knew that the newer build, it had some insulation upgrades to it, and it was a much more airtight building, and we changed that to 0.5. Well, let's see what happens if we do that. So we have 0.33 times 384. Now you could obviously do this as well. That 384 is the total floor space, but you could do that per room. So whatever an individual room is, if it's got a different air change rate, it might be 40 square meters or something of 40 cubic meters of a single room, times 0.5 or times 2, whatever it is, whatever that air change rate is for that room from the CIBSE guide, times your delta T and go from there. We'll try this one now at 0.5. So times 0.5 and then multiplied by our delta T. And you can see that's now only losing us 1,457 watts. So just by taking one air change of that off per hour, it's knocking our air change heat losses or ventilation losses down by a massive, massive amount. Now this is quite huge, and this is why it's very important to get that number there, the number of air changes per hour, to get that exactly right. And this is where it really can change, and this is where the debate goes on with CIBSE as to which is the numbers that we really use as real world numbers. But what we'd have to do, and this is where it gets quite incredible, and don't forget this was a big 5-bedroom 1930s property that had very, very poor insulation, and with these figures, the 17.9 and the 4371, we've done no window changes and we've done no loft insulation or anything like that. But you have to add those ventilation losses to the fabric heat losses to give you a total heat loss of that building of 22.3 kilowatts. So a little 24 kilowatt boiler, or a little 24 kilowatt gas boiler in that particular property that had no fabric improvements done to it whatsoever would absolutely smash the job. It would do the job, no problem at all, at design temperature outside of -2. So we know that works. So we can clearly see, what I've been trying to say for as many years as I can remember now, that we massively oversize gas boilers when you just don't need them. And this is a very, very large house that still only needs 22 and a bit kilowatts to actually heat it. But as I say, these air change rates are very, very important to remember, that we get this number of air changes correct. Now that is something that you're going to need to look at, because I think this is an ongoing subject, and this subject will change quite a lot. I have had a discussion of recent where possibly this constant may change, but that's the specific heat capacity and density of air under typical conditions. Obviously, if you've got more humidity, more people in the room, that kind of things, on a regular basis, that number would change. But this is what CIBSE standardise, if you like, and use as their constant as we move further forward. So that gives you a really good idea of what you can play around with that equation to get your different air change losses, and I hope that has helped you. Okay, so we just calculated the total floor area with one air change rate, and yet there will be many different rates. So that's just reiterating what we've just discussed. Now, this next slide is something that I think is very, very open for discussion, and something that I believe should be part of retrofit projects. In fact, I believe it should be installed in every single new build project, and I have no understanding and no idea why building regulations are not insisting on this technology being put into buildings. And of course, we're talking about mechanical ventilation and heat recovery, or MVHR, as is stated. A good friend of mine, Nathan Gambling, has got a wonderful podcast, which is the Beta Teach Pod. And he has been discussing this with two very good engineers, Barry Sharp and his father Duncan. There was it was one of the best podcasts I think I've ever listened to regarding this subject, and it proved all the points. It proved the points that I've learned over the years on MVHR, that the majority of them are just not commissioned correctly, or they're not installed correctly. And this is where we're getting, we can get a lot of failures with these units not working correctly. But many of the companies that are out now, there's quite a few. There's Zender, there's CVC Systems. There's quite a few companies that are out installing these products now, which are very, very good, and they're getting proven efficiencies coming back at 90% recovery. Now, there was a study done by the Passive House Trust that stated that, or initially stated, MVHR would only be viable in a property that had a ventilation change rate of less than 3. Well, that's been completely debunked from my understanding now. And because if it's balanced correctly and commissioned correctly within a building, it creates a neutral point. And so therefore it does recover that building and keeps a lot of the heat within the building before it actually runs to outside. And again, it's all about the commissioning. And so if you can recover up to 90% of that, let's have a look and let's see what we've got. So if we had 4,371 as we had, 4371.84, and we reduce it by 90%, we can remove 3,934 watts, so 3.9 kilowatts, off of that whole equation there. But let's play around with this to see exactly what we've got. So your air change rates wouldn't change necessarily from your fabric heat losses. So if we had our original unit of 6 kilowatts, that we'd done the fabric improvements and put the loft insulation in, and we got that heat loss or fabric heat loss down to 6 kilowatts. Let's then do our air change rates again, but let's just do them if we had the air change rates as they stand at those. So we're taking off 437. So if we have 4371, what's that? 0.84. minus the 90%, which is 3934.66. So that gives us 437.18. So we add that onto our 6 kilowatts. So we plus our 6,000 watts. So we have got a heat pump requirement of 6.5 kilowatts now, including your air change rates, and that's with MVHR installed. If we didn't have that, we would be looking at putting in around a 10.5 kilowatts of a heat pump that's going in. Now, if you then do MVHR later or afterwards, you've actually then rendered that heat pump oversized. Now, oversizing, as we've proven with Open Energy Monitor, doesn't present too much of a problem as long as it's only within around sort of 20% oversized for the building requirement that's there. But we still don't want to be spending out money on buying products and materials and plant that we just don't need. So I believe that MVHR is a really, really good initiative and a good technology to be putting into buildings. I've heard some very, very good stories about what it can do to air quality and children and adults, with asthma and that kind of thing like that their asthma pretty much gets cleared up in 6 months to a year because of the MVHR and the air quality that it can produce. No mold spores can be produced, and so you get very, very good air quality. You won't get any condensation on windows or anything like that at all. And of course, you're saving yourself quite a lot of money to do. But it is important, as if you would kindly listen to Nathan's podcast with Barry and with his father Duncan, that you'll see that the servicing of these and the commissioning is absolute paramount to be done. So filters need changing, fans need looking at and making sure that they're running at the correct fan speeds, and obviously each room that has your MVHR delivery points into those rooms to make sure that they are adjusted correctly for the cubic meter capacity of that room. So again, this is quite a short video, and it finishes up that last calculation. And I think for most people, you just play around with these figures, and you'll see that you can come out with all different kind of figures for air change calculations. So I hope you found it useful. And I'm looking forward to doing a lot more of these now. The next video, we're going to get on to mathematics of pipe sizing. We're going to be using the IMI Hydronics High Tools app, and I'll show you how to set all that up properly. I've learned an awful lot more about it in the last little while, so we'll be playing around with that for quite a few of these sessions. We'll get into valve KPA ratings, and we'll get into KV ratings, CV ratings, all that kind of thing, pipe sizing, and we're going to be doing some index circuits, radiator sizing. I've got a brand new idea of how to size radiators for buildings based on water volume. I have spoken about it previously before, but I'm going to go into a lot more detail with it, and we'll see where we go with this. But yeah, I'm enjoying doing these, and so I hope you guys are enjoying it as well. So if you do, please do give it the thumbs up. Please subscribe if you haven't already, and I look forward to seeing you on the next one. Many thanks. Bye bye.